share.
Hi everyone. So can you see the screen and you can hear me, right?
Yes. Yeah.
Okay, good. Yeah, great. Thank you again to the workshop organizers, and thank you all for coming together to share about teaching. So I'm going to talk about AIMD and flipped classroom teaching. And I think that there are two, they seem to be two different things altogether, but this is a very nice workshop in which I think they converge, okay, and I think we can learn a lot going forward. It comes in timely, this invitation to this workshop, because I'm dedicating this work to Professor Daming Chiu, who was one of the co-founder of AIMD, Additive Increase Multiplicative Decrease, on the occasion of his 70th birthday, which is next month. So we plan to have a hybrid celebration, okay, next month, December, okay. So this is the talk outline. I spoke to Professor Daming Chiu about this paper, and he gave me a few insights to what he did back then in the 1980s when he created this AIMD together with Rajan at IBM then. So what he mentioned was that in the early days of this internet congestion control, and actually we do have a few internet congestion control pioneers in our audience, for example, Fernando Paganini, right? So what happened is that in the early days, there were a lot of performance modeling. And so what AIMD really was about was a kind of abstraction. And I think this is where it comes in still important in our days. That means that how do we teach abstraction to our students? So I'm going to share with you a few teaching examples of how I use AIMD as a toy example to teach theory, in particular optimization theory, which would be very handy even to students who want to learn machine learning. And also this thing called Perron-Frobenius theory, which is a bit unfamiliar to many, but turns out that I think I'm going to share with you that it does have many applications, including AIMD. And this toy example could serve a very convenient way for us to integrate our beloved classical performance evaluation techniques and modern data science that are, forever evolving. So towards the end, I'm going to share with you this parallel between AIMD and this flipped classroom teaching, and to sort of walk you through this technology-enabled pedagogy that perhaps could help us to improve our teaching in this current environment of remote teaching. So I'd like to thank Daming, Tay, and Victoria, Srikant, Geoff at UCSD, Lorenzo, and Wong, and Stephen, and Stephen Boyd. So just now I mentioned about the importance of abstraction. So indeed, if we look at a lot of subjects that we have learned in the past during our PhD days, or even what we are teaching to our students now, we need mathematical modeling, right? And oftentimes mathematical modeling really means a form of abstraction, how it represents, approximates the real world problem. Okay, for example, we do have elegant queuing models, like what our the first keynote speaker gave to us, and oftentimes they are very good approximations of real world systems. But our students do realize that there is a trade-off between what they learn in classrooms, mathematical tractability, and also real world relevance. So how should we find this right match between the appropriate models and the problems that they have to solve? So this is indeed something that we need to hammer across to our students to prepare them ready for industry, for academia, for the real world. So really, right abstraction matters a lot. And not only that, it opens doors to new theoretical techniques. So in the following, I'm going to present to you using this AIMD two new, I would say they are still new, relatively new performance analysis techniques that have been developed over the last 20 years. Very, very exciting. And I think that they do really have potential to be taught in the classrooms. And the final takeaway from this, the importance of abstraction, is that it allows one abstraction to work or relate to other abstractions. Maybe one is good, the rest were developed by others, how they can come together. That sort of creates new ideas along the way, right? And also allows one to explore the trade-off between tractability and approximation. So AIMD indeed was sort of the abstraction, right, for this internet congestion control problem was laid out in this paper by Daming-Chu and Rajan, 1989. And so in the early days, as I mentioned, there were many performance models, but Daming mentioned that the important thing is that this AIMD wanted to present in that paper was that we do have a congestion control problem, but this is one problem in which we have social consequences, in the words of Daming. Okay, and so the idea is that the parties have to come together in a cooperative manner to arrive at a good solution. Okay, so if I look at this abstraction AIMD, indeed, it is turning a very complex problem into a very simplified one in which you could even visualize. Okay, and I think in that paper, the other very important takeaway is a picture, which really is very useful for our students, right? In order to assimilate, in order to digest, understand new ideas. Okay, for example, that picture, which is found in the next slide, this picture, right, is only for two flows, two traffic flows sharing a single bottleneck link. And I think it's found in many textbooks. For example, some of those listed down in the footnote over here, and also found in the paper. For example, Jim Caruso and Keith Ross, these very classical popular textbooks, and also Andrew Tannenbaum, used in many colleges and universities worldwide. Okay, and they have this picture illustrating why AIMD converges to a fair equilibrium, right, from any initial point. Now, so if I look at this picture, which is taken right from Daming's paper, I can consider this a visual proof. For example, additive increase corresponds to 45-degree, right, plots on this 2D plot, right? And upon congestion, that means that you assist this line over here, efficiency line, you're going to experience congestion, packets get dropped, and therefore both parties would receive that binary feedback, and therefore they would sort of draw back. And the way they draw back is that you draw a line, right, from this point all the way to the origin, locate the middle point, and that's where they would continue to do AI and so on and so forth. Now, so this is a very classical visual proof in that paper, very convincing, and I think we also see that in the classrooms. Now, here I superimpose on that diagram two things, right? In the following, the theory, for example, optimization. Perhaps we could optimize the bottleneck link in some sense, like, for example, controlling the efficiency line, for example, by some form of cooperation between the users and the bottleneck link. Another theory, which is the parent-Frobenius theory, captures exact details about this dynamical evolution. For example, if I look at this efficiency line, you see that here I plotted the W0, W1, and so on and so forth. Turns out that they are the iterates, right? On this efficiency line, the iterates corresponding to the output of a power method, the classical power method, right? And later you will see that it was also developed in the last 20 years by another group of researchers, right? And therefore we can really give a physical interpretation to the fairness line that was found in the paper by Daming, in the sense that this fairness line is like a direction. In other words, it is like an eigenvector. So it will be made precise in the next few slides. Okay. For example, the first theory, which is on optimization, then says, hey, can not just two users, but many users in this internet cooperate together to share a common single bottleneck link. And we know by now, right, through the work from Srikant, Fernando Paganini, and many others, right, Stephen Lowe, and so on, to see AIMD as solving implicitly a complex optimization problem. And so therefore, really, those feedback that the sources get, the sending sources get, are really so-called Lagrange dual variables and so on. So I think it provides a very elegant framework to see these very complex internet congestion control problems, right, through the lens of complex optimization. So here's the formulation. For example, maximize a sum of utility functions subject to linear constraints and so on. And what that theory embodies this so-called this theory, meaning this framework of network utility maximization, is to say that whatever algorithms that we design, whatever TCP algorithms we design, it corresponds one-to-one to a particular utility function. For example, in the case of this AIMD algorithm, it turns out that the utility function, as they work out through the math, is arctangent utility, right, which is like concave. So indeed, it converges, and I mean, from the algorithmic viewpoint, and to associate this AIMD with a subgradient algorithm in optimization theory. So that is for AIMD, for most of the TCP variants, such as TCP Reno, TCP Tahoe, and so on. And so using this form of a theoretical framework, later on researchers developed, including Fernando Paganini, fast TCP, which is to regard the utility as the logarithm utility functions, and then to develop in a forward manner new kind of TCP algorithms and so on. So this is a very exciting piece of research work that views internet congestion control as a form of abstraction. And it is very convenient because what I've just mentioned is really about just that layer, the congestion control layer. But in our, what we teach in networking is that we do have multiple layers. For example, the physical layer, the medium access control layer, and the network layer, congestion control layer, and then application layer. Each of these layers indeed can have their own form of abstractions. So abstractions would then coexist with abstractions, and they interact with one another. So if we go one step further, is to say that, hey, tell the students to say that, hey, maybe there are other ways to abstract, for example, application layers, and how would that in turn affect the congestion control layers and so on. So in other words, we are really dealing with cross-layer optimization networks, and I think this is a very nice way, for example, in teaching, to teach students to design optimization algorithms, let them know how to tune these optimization-based algorithms, and also to develop new data models. For example, through measurements of TCP data, they can create data models that approximate the real world, and these data models in turn could be verified through they do have tuning knobs that could then be optimized or integrated with this optimization framework. I think that this so-called network utility maximization framework provides a very convenient way to teach optimization theory, and how that can be related to machine learning is also of value, because it's not in the slides, but in the I think in the last 8 or 10 years, there were researchers at MIT who talk about computer-generated TCP algorithms, right? How can we use machine learning techniques to automatically derive TCP algorithms? And so I think this will be very exciting to the students. Now, that is optimization. And to the same problem, the same abstraction of AIMD, I could have another theory to teach students. For example, as I said, this is more unfamiliar to students, right? So-called parent-Frobenius theory, which is really about non-negative matrix theory. Now, turns out that there is another way to look at the AIMD dynamics exactly, right? And this was the work done by Abraham Berman, who is a non-negative matrix theorist, and also researchers at I think it's Ireland, right? Douglas and also Robert Shorten. In the last 20 years, they also proposed in this same article to promote AIMD for many other applications, for example, electric car charging and so on. Okay. So this body of theory says that we can view this AIMD, additive increase, multiplicative decrease, as I said, is only 2 parameters, right? How much to increase and how much to back off, fall back off. Now, so how should we connect these parameters for each user together in such a way that I could guide all of them, I could guide all the parties involved to a desirable equilibrium. For example, in that body of knowledge, they say that, hey, that AIMD dynamics really correspond to these linear systems of equation, right? So, for example, if you look at this particular linear system of equation. So it's like WK, think of it as the window, congestion window. It's like a n by 1. I have n number of users, right? And this A is so intentionally crafted, and it has this structure. It's like a diagonal matrix plus a rank 1 matrix, right? So if I look at the parameters, right? For example, the AI, you can find them here, the additive increase. So here you see I make it more general. You can allow, for example, each source to increase by arbitrary amount, okay? And each sending source can also decrease by an arbitrary amount. For example, this beta would be between 0 and 1. The conventional TCP will be, say, half, right? For example. Now, once I have all these things put together in this matrix, right? So it's sort of this particular matrix, its spectrum, everything is positive for this matrix. Likewise for the vector. So in other words, over here we have a positive linear systems. So the spectrum of this A governs the evolution of this vector W. And the nice thing is that, as I mentioned, it's all positive, not negative. So the parent-Frobenius theorem is particularly important. Okay. For example, we can show that, for example, this dynamics, I can essentially view it as a classical power method, right? Starting from any initial W0, okay, what happens asymptotically. And so asymptotically, we get the right eigenvector, right, corresponding to that eigenvalue, the largest eigenvalue of that matrix A. So indeed, it has this expression. And now, how can we teach this to undergrads? For example, I would say that, hey, we can simulate. There will be two implications. For example, back to that diagram, this one, right? We can shed new lights to a student saying that, hey, the iterates over here on this line, they are the outputs of that classical power method. And second, you really have a notion of direction, where to move towards. So this is where I plotted this arrow, like the direction, the eigenvector. And that's what eigenvector means, right? Direction. So if I want all these different sources to coexist with conventional, in other words, with conventional TCP flows, for example, alpha being 1, beta being half, then I can teach students to say that, hey, do some simulations. You can use different alpha, different beta, as long as they satisfy this particular relationship right here. All these different flows will converge to the fairness line, whereby all the sources share that bottleneck link equally. Okay. So I think this is a way to teach undergrads. I think they could understand linear parent-Frobenius theory because it is found in Google PageRank algorithm. It is used in Markov chain. And certainly, I think this is another way to allow students to appreciate the value of theory. So for graduate students, we can teach them more advanced versions. For example, that was linear parent-Frobenius theory. What if those alpha, the beta, they are nonlinear functions of the windows? Then we are talking about nonlinear systems. Then here, indeed, when I look at this, I'm very excited because I really want to do more research along the nonlinear versions of parent-Frobenius theory for this AIMD. Okay. But certainly there are more other ways for nonlinearity to come in. For example, machine learning techniques that coexist with those algorithms. They would lead to more complex dynamics and so on. And I think this is where nonlinearity matters a lot. So coming back to the last part, which is the flipped classroom teaching, what has AIMD got to do with flipped classroom teaching? It turns out that if I look at classroom flipping teaching, it is about getting feedback, active feedback from students. Very much like AIMD, the sending parties, they have no idea what the single bottleneck link. As teacher, we have no idea how our students are performing, what kind of backgrounds they come from. So can we engineer some kind of flipped classroom teaching tools to better equip the teachers to close the gap between the teachers and the students, right? So this is the parallel that I put in the paper, and I want to thank Geoff worker from UCSD in giving me this parallel. So it turns out that, for example, as teachers, we want to teach as much as possible, right? Subject to curriculum constraints and so on. But I think we should often ask, am I teaching too much? Am I teaching this, not enough? So in other words, what if I teach too much? Should I back off, like this MD? And we do not know what students can take in, right? At the end of the day, for example, so-called comprehension capacity, how much can they digest? So we oftentimes will ask, are students overwhelmed? Are they dropping behind? How should we help them? And if we want to introduce more advanced materials, are we going to do a slow start like TCP, AIMD? So here's the idea. We want to develop some kind of software to assist the teachers. So here the software is really built on top of this idea of so-called flipped classroom teaching, which is what I call it peer instructions, right? Peer instructions are pioneered by Harvard professor Eric Mazu and the Stanford professor Carl Willman, okay, 20 years ago, okay, peer instruction. So I think there's some value in peer instructions and so-called just-in-time teaching for our current remote teaching environments. So the idea is this. The idea is that for this classroom, flipped classroom teaching, we want to issue poll and quiz. And oftentimes there are multiple choice questions, okay? For example, during one lecture, we would have this poll and quiz routine placed at strategically at certain points in order to query the students to see if they are following along. Now, the idea of this poll is that it provides feedback in terms of statistical feedback, like histograms about what students have chosen. The quiz is related to that poll in some sense, right? So that students are not going to see this as a form of pop quiz. We want to sell this as a sort of low stakes assessment to students to tell them, hey, participate along, so that we can know how you are following, how you're performing, and so on. Okay. So this is a work that is published this year as well, early this year at ACM Learning at Scale. So here's a screenshot of the chatbot software that we have developed. Students get to see a poll. For example, this is a poll about the network utility maximization. They see a code, and they can then do it on their laptop, trying to code this thing up using CVX software, software developed by Stanford Professor Stephen Boyd, and then they can participate in the quiz, right? And right here you can see a histogram or pie chart, right, showing how many students have chosen option A, B, and C. So everyone can see that, and then those students who have made mistakes can actually learn from that. They say that, hey, I chose A, but the majority of the class chose B, so it means that something is wrong. And they sort of reflect and they want to know where they got wrong before a time quiz that comes, so before the time quiz comes in, they actually get like maybe 5 to 10 minutes to discuss before the time quiz comes along. So roughly speaking, this is what I call the poll quiz routine that I would then use from time to time in say 1.5 hour lecture. For example, like this is the Zoom screenshot. You can see then the students can use their phone, or they can use their web-based browser to access this poll quiz routine, and they would then participate along. So here in the next few slides, we just want to show you the data that we have. For example, indeed, students are very willing to participate along in this poll quiz routine. And I think how to incentivize students is important, right? Because there's a gap between the teachers and students. So how can we push the more able students to try harder quizzes, and to allow maybe those students who are not following along to at least try easy quizzes. And here's the sort of graph for these 2 years, 2019 and 2020, where we teach this course remotely, because 2019 it was social unrest in Hong Kong, right? 2020 was COVID-19, and turns out that students are very agile. They will answer the quiz even remotely, in a few days, even though it might be not timed in the sense, okay. And students then voted at the end. So again, through that software, to see how they like this sort of flipped classroom method, whether they want to have more in-class quiz or to have more outside class quiz, and so on. So I think from this, we can take away that a lot of students really enjoy having quizzes, both in class, like in the poll quiz routine, and also outside classroom quizzes as low stakes assessment. Now, to conclude, I think AIMD really inspires me to think more about flipped classroom teaching. How can we innovate and develop new forms of teaching methods? And I think this is very important because just like AIMD, we want to find the equilibrium, how much to teach, which I call content capacity, and to understand the limitations of our students, which is comprehension capacity. How to do that in a sequence of whole quiz routines, right? That is delivered over the semester. I think there's a lot more that can be done. And I think I'd like to share with you one last paper by Stanford, the Department of Chair, John Mitchell. He wrote last year in this conference, Teaching Online in 2020. He said that indeed, even teachers at Stanford CS, they mentioned about how hard it is to read a room. And so I think there's more that needs to be done for blended learning. So with that, let me end my presentation here. Thank you.
Thank you. And questions for Chiu Wei?
Hi. I'd like to ask if you have evaluated the influence on the big differences among students, culture, as among students' knowledge on this, because it seems you talk about a single class students, not a multiple class of students.
Right. Yeah. So here, do you mean the single class as in
homogeneous low level, homogeneous high level, or something like that? Yeah.
Right. So I think one thing that I like to bring out is that this idea of the peer instructions, that means using quiz and poll and so on, has been developed more than 20 years ago. And they were often very effective when they are used in person, right? Before we have COVID and so on, they are used already in person. For example, in the US, for large classes, they use so-called clickers. So indeed, you can view this software that we have developed as a form of clicker, digital clicker. But more to that, because if I look at what clicker has been used, they are oftentimes one shot. That means in that classroom, you use it for that day, nothing carries over. I think there's a need to view students' performance in class as a sequence. For example, how they are doing over time in that semester. If they're not learning more, if they're being overwhelmed, then maybe we should do something. And so in other words, we have to optimize a sequence of whole quiz routines or quiz assessments and so on over the course of the semester, rather than to just do it like what we have now with clickers, just like poll for that session, and the data doesn't carry over to subsequent sessions and so on. So to your question, I think indeed, I think when we have heterogeneous class, I think this may help. Yeah.
Thank you.
Yeah, welcome.